Underwriting for Autoline this week is provided by...
In this epic battle of fuel efficiency and endurance, we're here to see which hybrid has the best MPG.
That's the essence of a hybrid soul. But is there more to it?
The Hybrid Game MPG Challenge.
And now, here is your host, John McElroy.
Welcome to Autoline this week, where we're going to be talking about lightweighting, because that's a key thing that the auto industry is getting into right now, making cars lighter so that they're more efficient. There's all kinds of exotic materials being looked into, but guess what? The auto industry has not yet given up on steel. There's a lot more to go in that regard, and I've got three experts today to talk about it. Terry Cullum is the project director at the Auto Steel Partnership. Ron Krupitzer is the vice president of the Steel Market Development Institute. And Dr. Lou Hector is a technical fellow at General Motors and an expert in this area. And welcome all of you to Autoline this week.
Thanks, John.
Terry, let me start with you. I mean, it's right? Steel's got a long way to go yet.
Absolutely. My term for steel is it's resilient. I think when people were talking about its demise a couple decades ago, the steel companies quickly reacted. They knew their market, they knew their challenges, they addressed it, and here we are. Still working on steel solutions to help the automakers achieve lightweighting.
I guess I should say, steel going strong.
Yeah.
Oh, that's a bad pun. Ron, it's true what Terry just said. If you go back to the early 80s, I even reported on articles on this. A lot of people were saying, boy, give us another 10 years and cars are going to be made out of plastic, mostly. They knew steel was not going away. That never happened.
No, it hasn't. We have a 100-year history of vehicles made mainly with steel in the U.S. And I think that what we've seen is we've been challenged periodically over that time period, like you said, in the 80s, actually even in the 50s and 60s and 70s. And in most cases, our industry has been, as Terry said, resilient enough to come up with new solutions, new steels, new technologies that make steel still an important material for vehicles now and in the future.
Lou, these two guys, of course, come out of the steel industry, as it were. Mm-hmm. At General Motors, you guys look at all different kinds of materials, not just steel, but clearly this is a material that can be improved yet.
Oh yeah, most definitely. And we do, as you indicated, look at a lot of different materials. However, there's still significant challenges in trying to understand and actually model steels, especially some of the newer advanced high-strength steels. The steel industry has done an amazing job of coming up with new alloys that are substantially more formable than alloys that were developed years ago. And in the course of doing so, the microstructures and the subsequent mechanical responses of those materials have become quite a bit more complex. And our ability to model them and make predictions of how they're going to form are also in need of vast work and improvements, et cetera, and that's what we're set about doing on this ICME project that we're going to be talking about.
How interesting that General Motors, a car company, has a scientist like yourself, a PhD, doing basic research in steel. Why not just leave it to the steel industry?
I think that that's a very good question, but on the other hand, you have to have a conduit of sorts between an external manufacturer of materials in particular to the manufacturing and engineering groups in the automotive industry, largely because of the complexity of the business, but also the complexity of the material. So in probably one sense, I act very much as sort of a translator of, can we use these materials? How can they actually be used? How can we model them in our CAE models? How can we make predictions of them? And then work with our engineering and manufacturing groups to go over all that to make sure that they understand it and they can actually use the tools that we're developing to understand these materials.
I have to say that one of the greatest attributes, I think, of the car companies like General Motors and the steel industry is their ability to work together. For decades now, we have done probably the best work in collaboration. So we've really kind of broken down the barriers between supplier and customer in order to do things that are good for the industry, good for both industries, and really good for the consumer and the vehicle. And the research we do together through the Auto Steel Partnership that maybe Terry can explain a little bit leads us to common solutions that are almost turnkey, ready to apply in putting new steel technology in vehicles right now.
Terry, let's talk about some of that research. How long has steel been around?
Oh, forever.
Forever, okay. And yet you're still doing some basic research, and now the U.S. government, through the Department of Energy, is even keenly putting more money into that research. Why the interest finally in the U.S. government in doing some of this basic research?
I don't think it's, it just has come on all of a sudden. We have, over the past decade, worked on many DOE-funded projects that really were looking at what are the challenges to bringing these new grades of steel on board, getting them into production. And the steel companies have done an amazing job of coming up with newer grades, newer types of steel, higher strength steels. And so the challenge, quite frankly, is how can you take those new steels and actually put those into a manufacturing environment and addressed all of the manufacturing issues related to using those new high-strength steels. And really, that's what the partnership does. We really work on the manufacturing enablers so that when that new steel becomes available, then we have project teams work on all of the things that we need to know about forming, formability, tool wear, the things that absolutely count in the stamping plant and the manufacturing plants, so that those new grades of steel can not only get used, but they can get used very quickly.
Ron, you've been one who's been calling for more research in steel. Why the interest? As Terry points out, it's not all of a sudden, but why the greater interest on the part of the U.S. DOE in doing basic research?
Well, I think that our country, our government has realized that steel is an intrinsically valuable industry for the country. And technically, I think we are challenged by the world and the technical work that's going on all around us. So for the U.S. to be fully competitive, I think we have to be at least on a par with the research that's done everywhere else. I think that having an opportunity to work with the Department of Energy, recognizing the value of steel to our industry and to the economy is critically important. And so over the last decade or so, I think we've broken down some of those barriers, and we actually have done some amazing research, and we have a lot more on the table that will drive steel to even more productive use in the future.
Lou, what's some of that research? Can you talk about what
sure.
sort of things you're looking into, and what do you hope to get out of it?
Sure. The project that we have ongoing that's funded by the Department of Energy in part, and then the Auto Steel Partnership and through USAMP, is very much focused on developing an integrated computational materials engineering modeling framework for third-generation advanced high-strength steels.
Okay, now explain that.
I know that's that's quite a bit.
It's easy for you to say.
Yeah.
Integrated computational materials engineering, or ICME, is basically an approach that seeks to bring together experts in particular fields of multi-scale type of modeling to bring in the relevant microstructural phenomena happening at different length scales, integrate them together to produce, for example, a material model or a constitutive model that tells CAE forming engineers how the material is going to respond in response to complex loading, such as what we have to deal with in the automotive industry. But it also seeks to do one other thing. It also seeks to try to assist in the development of the material itself through better modeling technologies, such that the materials are targeted towards certain performance objectives that I think are extremely important for the automotive industry. So in the course of working on this project, what we have essentially done is we've assembled experts from 5 different universities. We have experts from the steel companies working with us, all contributing to try to developing this fairly complicated modeling framework that grasps the fundamental physics, mechanics, chemistry, and material science of what's going on in these advanced high-strength steels, and try to bring that to the point where CAE forming engineers and automotive engineers in general can actually use to make predictions and then ultimately understand how to use these materials.
So you're really simulating how not only the steel is made, but how it gets stamped out and welded and everything?
We're actually not simulating what I call primary processing, which deals with really how the steel is made. We're the end users of the product. We're not really into how the steel is made, at least not anymore. What we really do is we receive the materials and then we figure out how to use them in our automotive automobiles. So it's at that stage where we receive the materials, in general a wrought product. We have to figure out how it's going to respond. Can we use it? Can it meet our lightweighting objectives to meet the future CAFE standards, et cetera? So integrated computational materials engineering, I think in principle, was laid out very nicely in a 2008 publication by the National Academy's Press, and if I recall the title correctly, it goes something like Integrated Computational Materials Engineering, a Transformative Discipline for Improved Competitiveness and National Security. So therein lies a sort of a representative document that kind of lays out what integrated computational materials engineering is all about. But one point I also want to make is we have no models currently that would predict accurately, in my opinion, the performance of the types of materials that we're working on in the project.
And what we're talking about, I think, is that in the past, we've always developed new alloys for needs like General Motors needs new energy-absorbing, crash-resistant, high-strength steel. So we've had methods to do that, but mostly it's been empirical. In the laboratory, you'd make a number of different chemistries, and you make a different process, and you'd find something that worked, and then you'd scale it up to production. What Lou, I think, is talking about, and correct me if I'm wrong, Lou, is a more scientific basis on making those judgments about what are the phases and what are the mechanisms
in other words,
in the
less
steel.
Trial and error and more
Exactly.
predictive.
So really the holy grail of the whole thing, and we're by no means there yet, is to be able to give forming process engineers or anybody who's interested in designing a steel to meet certain targeted properties for implementation, let's say in a car body, a tool whereby that person could sit down and actually design the material from the alloy chemistry, from the microstructure, et cetera, as if that person were to receive that material in a tangible sense, but rather in the computer. Because we're not at that stage yet, the experimental aspects of what we're doing are critical for the development of the computational framework, and for that reason we have various universities working on contributing experimental data, as well as the steel companies working with us as well. So that's kind of the objective of the whole thing. So really the integrated computational materials engineering scheme, if you will, seeks to really combine in an intelligent way the most important modeling disciplines, starting with, in our case, quantum mechanics, to try to model line defects, which are basically dislocations, because plastic flow occurs through the movement and the interlocking of dislocations, et cetera, all the way up to the continuum scale is what a forming engineer would actually deal with. So you have these different length scales that we're dealing with, trying to build in the necessary physics to make the models more predictive. So in the future, there's hope and there's possibility of being able to have a tool that actually predicts new steel alloy chemistries, new forming processes based on steels that we don't have right now.
Wow, fascinating.
See, this is all about light weighting, and steel, as you know, is we're not changing the density of steel. Steel is basically 60% of the vehicle right now, and so to make a vehicle lighter in weight, we have to make parts thinner and more effective, more, certainly stronger for one thing, and thinner. So to do this and to handle all the processes of forming, it always becomes more challenging when you have a thin product. It's harder to weld, harder to form. And so having a model that predicts that, yes, we can create new properties that enable that to happen, and so you can reduce the weight maybe 10, 15, 20, 30% on a steel structure is enormously beneficial. So this tool in our project is actually going to be tested through simulation to validate if these properties that we develop in the model will give us the weight reduction we're supposed to get. So that'll be kind of exciting. And that's about year 4, I think, when we have to test that out.
Yeah.
And one of the additional benefits of the project is not just the modeling effort, which is going to really, I think, serve us well in terms of providing a very, very robust tool that we can use to do this predictive analysis. But we're also charged to look at developing third-generation grades of advanced high-strength steel. So we've got the steel expert team who are charged with doing just that, and the goal is to come up with a metallurgical approach or approaches to actually get close to the DOE targets that they've specified in terms of strength and elongation that comes very close to those third-generation targets And then we use those materials to input to the model so that the model is then validated on materials that we hope will be made into a production application as a result of taking us through this project. So this is sort of a 2-for kind of project.
There's been so much talk about nanotechnology and even talk about nanotechnology being applied to steel. This seems to be beyond that.
Well, I have my own personal opinions on that, and that goes back to 1903 in North Carolina at Kitty Hawk. When I worked at Alcoa, they became at one point quite interested in the history of the company. Anyway, to make a long story short, they came across a letter from Orville Wright in 1936 to one of the metallurgists at Alcoa who had inquired about the use of the alloy, aluminum alloy, in the crankcase for the Kitty Hawk craft, and it turns out it was an aluminum copper alloy. Well, you'll still see publications on aluminum copper alloys coming out in journals such as Physical Review Letters within the past 10 years that basically say, yes, aluminum copper alloys are consummate nanoscale materials. You have aluminum copper precipitates that block dislocation motion and hence contribute to the strength of the material. Steels are consummate nanoscale materials. I mean, just full of them. Even if you look at the structure of austenite and the size of austenite grains and steels that are known as transformation-induced plasticity steel. They're on the order of tens to hundreds of nanometers. So steels should definitely be included in whatever nanotechnology craze is still going on through the country.
And
because of that fact.
Would that work in the models that you're working on?
Yes, we have to address that. It's just that we don't necessarily stand up and say, aha, we're at the nanoscale. We just have to be able to make measurements at those length scales to get information from those length scales, for example, on flow properties of austenite, which tends to be a very, very small grain size, maybe 1 to 300 nanometers, into our microstructural models. So that's a real challenge. There's a lot of challenges associated with this, but steel, in many respects, is a consummate nanoscale material. It must be included in that by virtue of its structure, its microstructure.
There are so many phases, so many compositions, so many options in building a steel microstructure for a set of properties that without a model, we would be doing experiments forever. So the model is like a guidance, in a sense, based on science that'll tell us what are the more probable solutions to make the kinds of steels we need for the future.
I just hope the audience appreciates the next time you get a dent in your fender, just how much science went into all of that.
Exactly. Yeah.
Terry, where do we stand in the United States versus some of our major competitors? Japan, Europe, maybe even China. Seems to me like the U.S. is in a catch-up mode as far as research goes into basic steel.
I don't think we're in a catch-up mode by any stretch in terms of the technical development part of it. I think the big challenge, quite frankly, is the manufacturing capability. I mean, some of these areas that you're talking about, China and Korea in particular, they've started off with a clean sheet of paper in terms of building their greenfield sites to do these, processing of these advanced high-strength steels. We're working in a fairly old infrastructure, and we're creating, opportunities to update those facilities. So I don't think it's a technology divide. I really do think it's more along the lines of, the manufacturing capability and capacity just hasn't caught up here in the United States yet.
Terry's right. The number of steel companies that actually did business in the U.S. has shrunk, but the number of tons of capacity has actually grown. So we're still well over 100 million tons capacity here in the U.S. And in fact, most of our steel mills now have a global reach. And we are partners with and actually global steel companies at the moment. And so there's very little technology that we're unaware of here in the U.S. or implementing. And matter of fact, the offshore car companies that set up shop here in the U.S. typically source U.S. steelmakers.
Now, I keep hearing that with all this shale gas that we've got, that it's actually a competitive advantage to manufacture steel in the U.S. Is that the case? Can you buy steel cheaper here than elsewhere?
It's becoming more so. We're converting as much as possible our processes in steel mills to take advantage of the low cost of natural gas. And we project that that's going to occur for decades in the future. So it could be a great advantage for North American manufacturing.
Lou, what's the next step? You're heavily involved in this modeling. I'm sure there's a lot of layers to peel off this onion.
Yes, as a matter of fact, we're now working on the project in a very concerted fashion. It is moving along very nicely. And I think that one of my tasks as a principal investigator on the DOE project is to ensure that the I is happening in ICME, I standing for integration. Integration meaning that the people working at one length scale pass information on to a person working at the next length scale in a seamless fashion. This gets into issues that really go beyond technical because it comes down to the point that you have to have people working on this type of project who embrace a collaborative spirit. And fortunately, working with Ron and Terry, we were able to come up with this group, and they are now very efficiently passing information between each other without any objections or reservations at all to keep the project going and keep it moving forward. So I'm very pleased to see that happening. So there's really no lone rangers in this project whatsoever. Everybody's in it for the collective good of the project. So that's really my charge. But I work in different pieces of the project. So I actually do modeling work myself in addition to trying to help these two gentlemen run the project to the extent that I can. So I do make technical contributions as well as university visits. So,
John, we had 6 weeks to be responsive to a very detailed funding opportunity announcement out of the DOE, and we amassed a team of experts within our community, and the goal was to identify the best of the best. Because quite frankly, we knew we needed to have everybody working at their top level. And with Lou's help and Ron's help, the process yielded some really strong partners along the way. And we took time to make sure to cultivate the right team as we put the proposal together. And then when we were done at the end of 6 weeks, we looked around and we said, we've been successful. We did pull together the best of the best.
So Ron, you get this model at the end of the whole process, presumably. What will that allow you to do as the steel industry?
Well, I think it'll be a great asset to our researchers and the product developers in the steel industry itself, because it'll give them one more dimension in planning for how to approach the challenges that the car companies give us for stronger, lighter, more effective materials in their vehicles. And we have not seen that demand for increasing materials performance change in the last 30 or 40 years that I've been involved in it. There's always a need for a stronger, safer, more fuel-efficient vehicle, and we don't see that changing as we move forward, and materials will be challenged every step of the way.
Lou, what you seem to be saying is this opens up the opportunity to create even more varieties of steel, more grades.
Indeed, and if you have to look at the modeling from the standpoint that it is, to a certain extent, a form of experimentation, given that the modeling is accurate and grasps all the salient physics, chemistry, and mechanics of the material. But the one example I have in mind, and this goes back to my Alcoa days, is the development of the 25-pound beverage can at that point. It turns out that in this day and age, you cannot design improvements to that can or even can technology without the finite element method. So the finite element method answers a lot of questions, but it also gets one thinking about what could one do better. So really, what we want to do with this ICME project is get to the point where we have a modeling framework whereby we have modeled the fundamental microstructure of the material, a cube of the material, for example, accurately, and how that responds to implied loads. And then that gives a certain result, and then we can ask questions: if that doesn't meet the targets that we're looking for, what can we go back to do to change the microstructure in the computer such that we can get the performance targets that we want without going back and doing a lot of experimentation? Because the goal here is not to completely eliminate the experimentation. You're always going to have experimentation to validate the models, et cetera, but to minimize the amount of experimentation and get more quickly to desired results through these virtual thought experiments in the computer.
Ron, as you develop these new grades of steel, I would think that maybe you could also simulate new applications. And what I'm getting at is the SMDI recently showed a steel wheel, looked like a cast aluminum wheel, but it was made out of steel, virtually the same weight as aluminum, but at the price of steel, not the higher price of aluminum. Will this allow you to maybe model out other things that could be done in steel?
Yeah, absolutely. I think that what it does is it opens up the door to a combination of material science and design technology. We are now through the finite element methods able to do optimization of structures. When you make steel parts lighter in weight, you also make them thinner, and that reduces the stiffness. So we have to come up with design countermeasures to restore that stiffness or actually increase it. So the use of new shape methods, maybe tailoring products together that are different thicknesses that'll restore that stiffness, and possibly even using bulkheads or other designs that enable us to do that, can all be computerized. So we take the ICME, excuse me for using the acronym, output of this model, create a material with certain properties, then feed it into a design optimization, and we very likely will come up with something entirely new.
It's so interesting to see how much progress the automotive industry has made in reducing emissions, boosting fuel efficiency and safety. And yet we still are using the internal combustion engine and making the cars out of steel. It's just really impressive how many improvements have been made, and I'm sure there are more to come. With that, we're going to have to wrap this show up. I want to thank the three of you for coming on. Terry Cullum from the Auto Steel Partnership, Ron Krupitzer from the Steel Market Development Institute, and Dr. Lou Hector from General Motors. Thank you all for having been on Autoline this week.
Thank you, John.
Thanks for having us, John.
I want to thank all of you for having tuned in.
Underwriting for Autoline this week is provided by
In this epic battle of fuel efficiency and endurance, we're here to see which hybrid has the best MPG.
That's the essence of a hybrid soul. But is there more to it?
The Hybrid Game MPG Challenge.